All right, so before we really get started with questions from the chat room, I do want to address something. So there was a big reason I put up the discussion board I did Tuesday, and that was asking about what's entropy, what's Gibbs, what's Helmholtz, what's enthalpy, things like that, because coming into Chemistry 2, there's a lot of variables in terms of what you got exposed to in Chemistry 1, because we are required to teach calorimetry, but certain instructors go into the depth of teaching what Gibbs energy is at the same time, and there's also different ways people try to convey information. And because of this, we kind of see some misinformation creep up in Chemistry 2 when students start talking about thermodynamics. And sometimes these are honest misconceptions, sometimes they're misconceptions perpetuated by instructors, so there are a few things I want to break down. First of all, thermodynamics is not hard, it is daunting. What do I mean by that statement? Conceptually, thermodynamics is a thought experiment, and there are physical things that correspond to the different terms in thermodynamics. So enthalpy is a thing. It's the heat, it's both the sum of the heat, so any endothermic, exothermic reaction, you're measuring the heat, as well as just the internal energy, the U of a material. So that internal energy is the energy of the electrons, the nuclei, things like that. Gibbs energy is just a sum of all the different energies. It's the total energy based on the different contributions. So the example I typically give in class is debt. How much debt are you in? Well, there's credit card debt, there's mortgage debt, there's student debt, there's car loan debt, but there's also things that detract from your debt, like the value of your checking account, the value of your savings account, any savings you have, things like that. So Gibbs is meant to represent the sum of all the different energies that an atom or a molecule or a system has under constant pressure, and Helmholtz is the same thing but under constant volume. So that's the first misconception. Thermodynamics is just kind of this abstract idea. It's actually very rooted in practical things because it came about in the mid-1800s regarding the steam engine and the Industrial Revolution. These are engineers, and I liken engineers to speaking a foreign language. Engineers are good at math in a practical sense, but if you really understood mathematics and you understood physics, engineers sound like slack-jawed yokels when they discuss math because they're not actually truly mathematicians, and they try, but they're not very good at describing things mathematically. They're very practical. The second, and this is one I've seen a lot on the discussion board, a lot of people are saying this: entropy equals disorder or randomness or chaos. And the thing is, it doesn't equal any of those things. It's not randomness, it's not disorder, it's not chaos. And the way this misconception got started was, it's like a game of telephone. You had somebody explain something to someone who didn't quite understand it, so they explained it to someone else who didn't quite understand it, and this is how we get to the disorder equals randomness. So first of all, entropy is not disorder. We can disprove that a few ways with just thought experiments. One is, let's say I write up a series of numbers. So I've got 1.414, I'm going to write them out for you, 4, 2, 1, 4, 1.73, 25, or 2051, and 2.718282, trailing on to infinity. Now, most of you watching this video would say that these are random numbers, even though you know I'm about to tell you that they're not random numbers. So, what are they? Well, this is the issue of using randomness and disorder and chaos as definitions, is that just because you don't understand what these numbers are does not make them random or chaos or disorder. This is the square root of 2. This is the square root of 3. This is the exponential, and I can write 3.141, trailing off to infinity. And it's the same thing. So the issue is that random and chaos and disordered are subjective terms. Some may think that something is random or disordered, but that's simply because they may not understand the root mechanisms. So that's your first disproof, is that you're using a word that's subjective. Now, you could also kind of argue that's a semantic argument, it's not a real argument. Okay, fair enough. The second disproof: if you claim that it's randomness or disorder, and most of you have acknowledged that the universe is going towards higher entropy, here's a problem for you. What has more disorder, more randomness, a gas or a solid? And immediately you'll say, well, the gas has more disorder, but keep in mind that if the universe is increasing its entropy, The universe started as a gas. Like carbon, silicon, all the heavier elements were a product of the sun's undergoing nuclear fission. So our planet would not have existed at the start of the universe. It was nothing but hydrogen stars. So if the universe is increasing in entropy, why is it forming more and more solids which have less entropy? That would mean the universe is actually moving towards more order, not more disorder. So again, you're kind of seeing how this order-disorder argument doesn't make sense in the context of how it's been taught to you. So what is entropy? Well, there's 3 levels of definitions. And I say 3 levels of definitions because there's the true definition is that entropy is the number of microstates. And there is a video on the course website under lessons. It's done by PBS Spacetime. He does a very good job of explaining this idea of microstates. But this was the Boltzmann's definition. S equals K ln of omega. So K here, and I actually should have a little subscript B, is the Boltzmann constant. S is the actual entropy. So again, if you're going to define entropy as randomness or disorder, I challenge you, how are we able to quantify disorder? Because we're not quantifying it relative to order. We're actually quantifying the amount of disorder to like hundreds of decimal points. Omega here, though, is your number of microstates. Now, a microstate is a way of arranging a system. So if we only have one way to organize a system, omega is 1, natural log of 1 is 0, so entropy is 0. And this is how we get the lower limit for entropy. If we have a perfect crystal at absolute 0 Kelvin, there's only one configuration available to us because all the atoms are in the lowest energy state. There's only one way to arrange the system, so the entropy goes to 0. Now, if we have more than one way, you may sit back and say, well, it's random. They can go to any of those orders. Not quite. All of those microstates have to have the same energy. So let's go back to the example of the square root of 2. 1 point, bring it back up. 414, 214. And you may argue, well, it's just random numbers. Well, it's not really random numbers because we have the restriction that if we square this number, we have to get 2. So because we have this restriction that we square this number and it has to get 2, it's going to specify what the number is. Now, the point of an irrational number is that, you really have to do the work to predict it. You're never going to get a repeating pattern. So it's kind of like this. We do have a restriction on what those microstates are. Their energy has to equal the energy at a given temperature. But entropy means that we have a lot of different ways we can arrange the atoms to get the same energy. And that's the idea of entropy. It is, if you want to work with this definition, you understand, that's fine. But the way I prefer to define it for students is this: degrees of freedom. So basically, how many restrictions are we putting on the atoms? If we have a perfect crystal at absolute 0, we specify the temperature, and because we're in a crystal, we've specified all the positions. So there are 0 degrees of freedom associated with those atoms because their positions and vibrations and all that information is fixed at 0 Kelvin. Now, if we have a solid, there is some freedom associated with that solid because the atoms do vibrate around due to heat, but those vibrations are very limited in how far they can go. You can't get too far, especially if you're a crystal, you can't get too far away from your crystal position. So it has some freedom, and this is why when we heat up a material, its entropy increases, but it's not going to have as much entropy as, say, something like a liquid, because liquids flow. And because they flow, the atoms do have some flexibility in where they are in the solution. They can't go too fast, and they can't go too far, but they can definitely flow past each other. Now, if we consider a gas, gases, particularly low pressure, high temperature gases, the atoms have effectively no restrictions on which ways they can go. And this is why we would say a gas has a high entropy, is that there are no constrictions on where those molecules can go. They can go until they hit the wall of the container and bounce back. Now, how about a mixture? Why does a mixture have an high entropy versus 2 separate liquids or a liquid and a solid? It's the same thing, that in a pure liquid and a pure solid, particularly if you have pure solid as a crystal, the atoms are limited by who they can associate it with. Whereas when you put a mixture together, the atoms can associate with themselves. So if your liquid is water, the water molecules can associate with other water molecules. And if you have something dissolved in the water, they can interact with those as well. So this is the better definition of entropy, is degrees of freedom. How much are we constraining the atoms? the less constraints we have, the more freedom the atoms have, because it does take energy, or we have to basically force the atoms into a given position to reduce their freedom. But this also explains why increasing entropy is more favorable. The more degrees of freedom you create, the more option these atoms have, the less constrained they have to be. So this is why the universe is marching towards increased entropy, is that it is increasing the flexibility of the atoms and therefore lowering their energy. It takes energy to constrain atoms in low entropy systems. Think about it this way. If you want to cool something to absolute zero, you have to pull all the heat out. There's a lot of work involved in that process. This isn't true at something sitting at room temperature. It's easy to maintain something at room temperature because everything around you is at room temperature. Now, the other one, what I'm saying, it's a tautology argument that people are using. Why is defining pressure and defining volume important? And they keep saying, well, it specifies the variable, but that's kind of a tautology. We have a variable, a given specified pressure or variable or temperature, pressure or volume. So Gibbs is constant pressure, Helmholtz is constant volume, and they say, well, it specifies which variable we're working with, and our variable is specified by constant pressure, constant volume. It's not really what we're going for here. A better way to look at it, and this is why we need the Gibbs versus the Helmholtz, is that for any thermodynamic system, we have a system surrounded by its environment. And sometimes this is very well defined what the system and the environment are, sometimes it's not. So when we do calorimetry measurements, the system is whatever we're trying to measure the heat capacity of, and the environment's whatever's inside, whatever liquid we're using the calorimeter. It may be poorly defined. So if we have something like a reaction going on in water, we have mixing acid and base, or both in water, mix them together. The water is the environment, the system are the individual acid and base molecules, but it becomes really hard to define where the edge of it is. The big thing here is that our system and our environment exchange energy two ways. One is through heat, the other is through work. Now, if we have a piston, and this is basically what the system is doing, if we have a piston, your piston is a fixed container with a pad on the end to push or pull. If the piston has a fixed volume, it can't do work. And so this is the distinction between Gibbs and Helmholtz. Helmholtz, F, is a constant volume. And because of that, our work term is equal to zero. Our system and our environment can only exchange energy through heat, through Q. With Gibbs, we're under constant pressure. And because of this, our work term doesn't have to equal zero. The system can expand and contract. And this has implications about basically heat. What does heat do? If we're underneath a constant volume situation and we heat it, all that heat goes into the internal energy. And so a lot of you have this definition, delta H equals delta U plus delta PV. For the Helmholtz term, this term equals zero. So any heat we get, because typically delta H here is going to be connected to our Q, any heat goes directly into the bond energies and the energies of the individual electrons. If we're underneath constant pressure and we begin to heat, we can also do work. So the system may expand in response to this heat. And so not every joule of heat you put into the system is going to necessarily go into raising the temperature. It may also go into doing work. So this is a big distinction to make between Helmholtz and Free. Helmholtz had constant volume and Gibbs at constant pressure. Constant pressure, we can do work. At constant volume, we can't. And this is why we need to make that distinction, because it makes a very important statement about what the system and environment can do to exchange energy. And in fact, we can get the Q equals zero case too, and this is what's called adiabatic. So for adiabatic systems, Q is zero. And this means the only way the system and environment can exchange energy with each other is through work. So yeah, these are just kind of the common misconceptions I see, but again, that was the whole point of the discussion board for Tuesday, was to see kind of where you all are. You're going to notice discussion board that's due tomorrow. This is Hess's law. You technically covered it in Chem 1. That said, Hess's law is a particularly involved and daunting process. And so please consult the videos online. Please consult the notes. You are going to have a Hess's law problem on the exam. You're also going to have one where you can do Hess's law based off tables. You're going to see examples of both of those in the packets. Big thing is that you're not going to see examples of this in the web assign. When you look at the problems, you're going to kind of figure out why pretty quick. It is hard to program those in a web assign. On top of it, there's a lot of intermediate steps. If you get the intermediate step wrong, you're going to find that it kind of propagates and it's hard to diagnose where the issues are. So this is probably where you're going to want to send me questions for the live streams so we can talk about how to work through a Hess's law problem. But that's all I really need to talk about today. Again, there's just some common misconceptions about thermodynamics. Entropy is the big one I keep seeing. The relevance of pressure and volume is the other one I see. And also just kind of this idea, I'm seeing a lot of technical definitions. These technical definitions are great, they are correct, but they don't necessarily reflect that you understand what these terms actually mean and what they connect to. So if there's anyone out there, are there any questions just in general or any questions you're having right now? Correct. So the question I got asked is Gibbs more related to problems where the constants are temperature and pressure? Helmholtz sealed vessels with temperature and volume are an issue. So one or the other is a constant. Correct. The idea is chemists like to work with Gibbs because most experiments are run open to the air, and so your air is at a constant atmospheric pressure, and that's where we get that Gibbs relationship to say that if it needs to expand at constant pressure, whatever reaction we're running with will. Bomb calorimetry, which is where we get a lot of numbers for heat capacities, Oh no, you haven't. I've just been talking to myself, so don't worry about asking questions. Um, Helmholtz shows up in two different forms. One is for bomb calorimetry, where it's a sealed container where we measure heat capacities. In that case, we only have the heat term. The other is more computational chemistry, where they're doing a lot of their simulations in a constant volume system. There is a way to translate Gibbs to Helmholtz and back and forth, but traditionally what we're going to work with is Gibbs because most of our experiments are open to the air. And that keeps us at a constant pressure, but again, that makes implications. So the heat capacity is the big one. If you heat a solid under constant volume, it heats it faster than if you heat a solid at constant pressure. Because what will happen to the material that's under constant volume is that none of that heat's going to expand the material. So if you take something like a liquid and you heat it up in a sealed container, it will raise its pressure trying to push out the glass or push out the container. And that's why heated liquids in sealed containers are so dangerous. They don't have that work term to push out. But yeah, that's the only difference between Gibbs and Helmholtz, is just whether you're keeping pressure constant and volume constant. It makes implications about how energy is exchanged, but that's the only real difference between the two. So the reason why your pressure cooker cooks food so fast is more an issue with vapor pressure. So typically you're cooking in a pressure cooker with a liquid, with water, and the temperature of water can only go to 100 degrees C at 1 atmosphere. So what your pressure cooker does is it lets the pressure go up and up and up, and basically it doesn't let the water boil. So as the water gets hotter and hotter, it never reaches atmospheric pressure, so it never boils, so the water is allowed to get hotter, which is why it cooks things faster. Now, in terms of problems using Gibbs or Helmholtz, this is going to be kind of reflecting on like the homework questions where it says, okay, given the following delta H, delta S, and T, find the Gibbs, or given delta G, delta H, delta S, find T. Basically, you've got the Gibbs equation. Delta G equals delta H minus T delta S. You can be given 3 of the 4 variables and asked to solve for the 4th. You'll also see this show up with the Hess's law problems. So with Hess's law problems, we can use Hess's law to find delta H for a reaction and delta G for a reaction. And typically when we want to find delta S for a reaction, we just use this relationship. And that'll give us the delta S of the reaction. There is a Hess's law expression for delta S, we just traditionally don't use it. Because if you've gone through this work to find delta H and delta G, you might as well just use the delta S that falls out of it. But I would say those are really the only forms you're going to find. Also, the other one we're going to see, and this is a little bit ahead of where we are right now, your equilibrium constant, KQ, is e to the minus delta G over RT. So if I give you KQ, you should be able to find delta G, and vice versa. If I give you delta G, you should be able to find KQ. Now, Helmholtz, sorry, I forgot to mention this. Helmholtz, I'm going to mention it so you're aware of it. We're not going to focus very much on Helmholtz at all in this course. Just be aware, and it's something that does kind of get left out of the discussion. Gibbs is not the only thing. There's also Helmholtz. There are a lot of parallels between Gibbs and Helmholtz. They're effectively the same thing, just constant pressure versus constant volume. But do be aware there's more to the world than Gibbs. That is an option. So what's taught to you probably in Chem 1 is the idea you can add and subtract reactions. I will always give you a problem where that is possible. That said, that is not how it's done practically in the real world. What's done in the real world is that you would write out the Hess's law expression for each reaction and then solve for the unknown variables. So, yeah, if you have any reaction, Hess's law actually says the delta H of any reaction is the sum of the products minus the reactants. So this is a pretty intimidating looking equation. It's just intimidating because of how we write things mathematically. It's not actually meant to be that bad. So let me bring up a problem. And I would say the Hess's law problem on your exam, next exam, is probably the hardest part of the exam. So I'll show you an example here. So this is one of the packet problems. So we have 2 calcium plus O2 goes to 2 calcium oxide. And this says a delta G here, minus 1207. Calcium carbonate, CaCO3, decomposes into CaO. Plus CO2, the delta G here is 130.9 kilojoules per mole. Carbon plus oxygen goes to CO2. The delta G here is minus 394.4. And then what we want to know is the Gibbs free energy of 2 calcium plus O2 plus CO2 going to 2 CaCO3. So the way you would use Hess's law practically in this case is that we know that this delta G here, and we can swap out G and H here, is just the products times the reaction coefficients minus the reactants times the reaction coefficients. So we've got 2 times the Gibbs of formation of CaO minus twice the Gibbs of formation of Ca plus the Gibbs of 1 times the Gibbs of formation of O2. And this is all going to equal minus 120, or yeah, minus 1,207. Now, the reason why we want to work with the Gibbs of formation, the delta G of formation, is this is the energy gained or lost making something from its elements at room temperature in 1 atmosphere. So the delta GF, I'm going to erase it off the top of here. Is defined as, for something like O2, it's the Gibbs of making O2 from O2. So this would be 0. So the Gibbs of formation of any diatomic gas, O2, N2, F2, I2, Cl2, Br2, H2, are all going to be 0. It's also going to be true for any pure element. So if I'm making if I've got calcium, the Gibbs of formation is also 0. And so then I can get the heat of formation of any compound. So compounds don't have a 0 Gibbs of formation. There's Gibbs energy gained or lost to make CaO. But what we can do is that for each step of each of these reactions, I can write out these expressions, solve for the unknown variables, and then once I know them, I can plug them back into this equation and solve. But that's more practically how it's done. That's the types of calculations I used to do for my thesis and PhD work, postdoc work, is you would use a Hess's law expression. So adding and subtracting reactions, it's in books teach it, but it's never ever done in practice. You will never see it outside of like a chemistry 1 classroom. This is more what you see in the real world, and on top of that, if you go to the front of those study packets, and I'll share the screen with you just so you can see it. These heats of formation and Gibbs of formation are what are called state functions. They only depend on temperature, pressure, and molar volume. Because of that, once we know them, we don't have to solve them anymore. So this delta H F naught for Al2O3 and this delta G F naught, these are physical constants for these materials. So in principle, and you'll see this for thermodynamic problems with tables, you just go to the tables and look these up. And from there, you can just calculate this directly. That's more what we're trying to get you to at this level of chemistry, is that adding and subtracting reactions is fine. Again, all the problems you're going to see, especially on the exam, you can add and subtract the reactions to end up getting the final delta H and delta G. Practically, though, this is the one you need to become more comfortable with, because this is how it's actually done. And what I can do in the next live stream is I can just start working with these problems to give an example of how to do, how to use Hess's law to find a heat of formation or a Gibbs of formation for an unknown reaction based on the other reactions. Again, this is the more intense, like this is a large portion of the next test to be able to do these types of problems. But if you were taught adding and subtracting, you're going to have, those will be solvable by adding and subtracting reactions. I just don't advocate for it because it's putting you at a disadvantage when you go out and actually do the problems. Yeah, what we'll do next time is I'll just start out. It'll take me some time to write it out, so it'll give me time to write it out big and legible behind me, instead of just kind of trying to do it on the fly. And yeah, what we'll do next live stream is we'll work one of the big problems. And again, like, I teach problems both ways. Um, Again, I kind of understand, depending on who you have for Chem 1 will dictate how you were taught how to solve these. Usually what I find with students is that they find this method of solving Hess's law directly actually isn't that bad. It always ends up with an algebraic expression, and most of the thinking is taken care of for you. So really, it's just a matter of manipulating algebra more than anything else. There's just a few things you have to keep in mind when you do it, but it's very automated. It's a very automated process. My issue with adding and subtracting, I think for students, the problem is that sometimes you see one and it's kind of clever how you flip it around, or it's kind of clever how things cancel out. That can be an issue, is that maybe you're just not having a clever day, and you go to take the test and realize, like, oh, I can't figure out how to add and subtract these reactions to get it. You're not going to have that issue with writing out the Hess's law expression. It's a very automated process. But again, yeah, next time when we start up, that'll give me time to write the reaction up on the board, make it big, clean, legible, and we'll work through an example. And for the delta H and the delta G, it's the exact same setup for the Hess's law. So what we're going to do tomorrow will be the delta H. If you want to do the delta G, you just switch all the H's to G's and use the G numbers. Personally, I think it would be ideal if we got away from teaching you the add and subtracting and just kind of started you out with the Hess's law with tables and then kind of worked you up to the bigger problems. Just because I don't see the merit in teaching you adding and subtracting. Again, I did these calculations for years. You're not going to see adding and subtracting reactions because it presupposes that you've got that information. In most cases, you don't. But as far as information about the heats of formations of solids and liquids and gases and all these materials, I've got a nice big fat book I stole from Stanford that's got all the information in it. In fact, actually, if you're curious, you can go look at what's called NIST-JANF, NIST-JANAF, and they have all the tables for these materials. Yeah, that's like the 1/2 or the 3/2 or something like that. Like, it's, I mean, I teach how to do it, but it's, especially if you're given like 5 reactions, it's like, okay, there's a lot of cleverness that goes into those. Like 3 is usually manageable, 2 is really obvious. Once you start getting to like 4 and 5 reactions, it gets really hard to see what you're doing. And again, the second method, it's very automated. Write out Hess's law, cancel out everything that's 0, and then just start solving. And you don't end up with a quadratic or anything. It's always just simple algebraic expressions. The hardest you can get is that you have an equation with 2 unknowns, and you have to solve for one of the unknowns in another reaction. Particularly with my problems, you'll start picking up on the flavors of like where I bury those numbers at. But we'll go through both methods too. I'll talk about how to solve it by adding, subtracting, as well as by doing the straight Hess's law expression. And there are a lot of practice problems on those study packets. And the delta H and the delta G are kind of repetitive problems. As you're going to find, there's a big reason for this. The last page asks you to solve the delta S for each of those reactions because in principle you've solved the delta H and the delta G for each one, so you've got that Gibbs relationship. Delta G equals delta H minus T delta S. But if you can do those problems, the ones I give on the exam are 3 reactions. So they're meant to be very doable in the time frame. Like, you'll definitely see in the practice packets there's like 4 and 5 reactions. I'm not going to give you anything that ridiculously hard. Even the key is kind of like, I had a good day one day when I figured one of those out. But yeah, the exam is definitely going to have Hess's law, but I'm not going to give you anything ridiculous on the exam. Other questions? Oh, before I forget, also an update for y'all. We are, because of COVID, we are not giving withdrawal fails anymore. We're not giving WFs. If you withdraw from the course anytime you were given a W or a WE, neither of which counts against your GPA. So hopefully that will take some stress off of y'all, particularly if you're worried about like, well, what if I don't do well in this exam or the next one? Well, you can always withdraw the course pretty much up until the last week. I'd ask you not to wait that long. But if you definitely do like test 2 and test 3, like, oh, I'm not doing great, and then you don't do well in test 4, you can withdraw the course without penalties. So you've already paid for the course, you might as well just stick out the entire course. Don't bother with the final, and I'm going to just tell you that because there's no point in doing the final if you're just going to withdraw from the course. Also, if you take the final, I have to enter your grade in. So from this point on, I would say just kind of stick it out. Regardless of what your grade is. If anything, you're just going to get exposure to the material. But traditionally what happens is that we have the 60% mark, and if you stay beyond the 60% mark and you withdraw the course, now it's a withdrawal F, WF. And so that counts against your GPA. We are not doing that this summer. I think they're not even going to do it this fall. But definitely this summer we've just been given the email saying there's no penalties for GPAs. So again, take the exams. You can withdraw at any time. If you get to the end of the course and you say, oh, I'm not happy with my grade in the course, you can still withdraw. You don't necessarily have to be passing or failing the course. So yeah, take that burden off knowing that you don't have to make the judgment call now to know if you're passing or failing the course. You've got until the day the final exam is due to make that choice. But again, please, for my sake, if you decide, hey, I'm just gonna drop the course because I'm not getting the grade I want, do that like the last week of class. just because it makes your withdrawal paperwork a lot easier. It's a lot more complicated if you decide to withdraw the absolute last day. But yeah, you have that option. So yeah, I would say stick with it if you can. So for this fall, Chemistry 1 and Chemistry 2 are online. Orgo 1 and Orgo 2 are going to be hybrid at this point. Now, again, this is all contingent on whether or not North Carolina goes back to phase 1. That's hard to say at this point. But right now, we are planning courses with the assumption that Orgo 1 and Orgo 2 are taught hybrid. So you show up for lab and that's it. Everything else is online. Chemistry 1 and Chemistry 2 are definitely going to be taught online. If you do the Orgo option for the fall, the labs are capped at 8 students per lab. So each student does their own lab. We're going to require masks. We're still trying to figure out how this works out, but we're probably going to provide you with masks if you don't have one. We're also going to go do temperature checks at the door. You're not going to have a lab partner, but we concluded with organic that beyond the issues we're having right now at Carolina Biological, an online organic lab is functionally useless. There's like 4 labs you can do at home, and they're like stuff you would do in like elementary school. So we're going to require the labs for organic because organic, if you are doing organic lab, it's required for your major. Odds are you're going to be in a lab setting. We want you to learn how to do the techniques. You need to learn the techniques or you're going to be at a severe disadvantage down the road. So yeah, that'll be the thing with organic. It's for South Campus where I teach, there's going to be labs 3 days a week for the Orgo 1 and I think 1 day a week for the Orgo 2. I'm not sure how it's going to happen on North, but I know that they're going to be teaching Orgo courses on North Campus as well. So you're going to have both options for campuses, and again, it's going to be hybrid for the Orgos. As far as other classes go, my guess is that they're going to be online. What Wake Tech is afraid of, and they're legitimately concerned, if there is, for whatever reason, we go back to an earlier phase, we don't want the same problems we had in the spring, which was we were seated for half the semester and then suddenly we went online for the rest of the classes. We don't want to do that. My sinking suspicion is that that's going to happen to State and UNC, is that y'all are going to go back. There's going to be an outbreak and suddenly you're all back home doing online courses again. We don't want to put students through that. So if it can be taught online, we're going to do online. Because the other thing is you also have to get instructor consent for us to teach hybrid courses. So we cannot be compelled to teach seated courses if we don't feel safe. I opted for it. I think I'm going to be just fine. I'm going to do the mask and everything. But most instructors are not willing to go back to a seated classroom, particularly when there's no vaccine on hand. I mean, our health insurance is good, but we'd really rather not test that hypothesis. So yeah, hopefully that answers your question. But I would say pretty much unless it's required to be online, and again, that's a small number of courses, or required to be seated, which is a small number of courses, Wake Tech's going purely online. Yeah, State's playing an interesting game right now. From what I understand, they're trying to do, maybe I'm confusing this with UNC, but it seems like they're only trying to do the freshman and sophomore courses seated, and the junior and senior courses are online. Yeah, we're not sure. We know what's driving UNC and NC State to bring students back. We're not underneath that type of financial pressure. They are. But I kind of agree with their own position that said that they are simply not equipped to handle students coming back. But again, we'll see. Again, I don't see how you have someplace like Regal Hall where there's like 8 students sharing a bathroom. Cutting that down to 4 students does not slow the infection at all. You still got 4 people sharing a bathroom. Even Wolf Village, even if you cut that to half capacity, that's still 2 people in a room together. And yeah, with the way the dorms are laid out at State, if there's a single student who comes in sick, particularly during move-in, a third of the campus is going to be infected. I'm not sure what NC State's testing capacity is, but a lot of their recommendations kind of come across as they sound great, but they're not practical. Like taking students' temperatures at the door, like that's great, but if they're sick, they've been sick for 2 weeks. I think it doesn't help that North Carolina is also like starting to ramp up in cases, confirmed cases as well. So hopefully State's going to start playing a more conservative game, UNC as well. For us, our decision to stay online was purely motivated out of student safety. Yeah, I mean, it's the online version is not helping for your universities because students in your case, like, why would I go pay to be in a dorm when I'm going to take the course online? Like, why would I physically show up? And NC State and UNC make a lot of money out their dormitories, so them not being filled is costing them a lot of money right now. Their research programs aren't doing research because it's so hard to deem someone an essential person. And again, I mean, I'm going to tout Wake Tech. Like, we care about our students. That's why we don't want you coming back. But on top of that, we also kind of acknowledge, like, y'all need to plan your futures too. And so the decision to go hybrid was made this week. And we're going to stick with the hybrid decision because, again, we don't want to change our minds at the last minute. The hybrid, we're pretty much locked into at this point. There would have to be a good case made against it. But, yeah, we don't want to put students in that position where, particularly our students, don't have dorms. So let's say you want to go to Wake Tech, you rent an apartment in Raleigh, Wake County, suddenly we're online. Why did you bother to come to this county? We just don't want to put you all in that position. And I say this as an NC State alumni. Like, I love my alma mater, but, like, they're kind of like Disney. I mean, there's money to be made, so. Yeah, I hope it works out for you soon. I hope NC State finally nails down what they're going to do because we're kind of, we get to hear what's coming down the chain of command, but NC State and UNC are so weird to deal with. We set our schedules around theirs, and so for them to constantly be changing their ideas doesn't help us at all. And part of the reason why we start so early and finish so early is so that when students transfer to these schools, they have their grades well ahead of registration deadlines. Yeah, you're very welcome. I'm trying to be very transparent with y'all about what's going on. Like, there's no need to like hide any of this information from you. Also, to kind of like push our organic program, like organic instructor. I'm the organic instructor on South now. We have an organic instructor on North. Like, consider that when you're considering organic versus state. I mean, I took organic state. There's a couple good instructors at state. I shouldn't say that. Like, I'm fraternity brothers with a lot of professors at state, but the organic program has an interesting reputation. We'll leave it at that. Actually, my favorite question out of state so far has been, and I saw this on a discussion board, how are they going to handle the wolf line? Because those buses are always packed. Yeah, again, I love my alma mater, but man, some of those chemistry instructors are very interesting. We did actually have a little spat with NC State's chemistry program once, and nothing came of it, but it was very interesting to see them tell our students that they needed to retake courses at state. It was like, that's not how transfer credit works, but okay. Well, hopefully we can, in spite of COVID, make this a good experience for y'all. It's 12:28 now, so I'll go ahead and start signing off. Thank you all for showing up. Thanks for the discussion. What we'll start with next week, or tomorrow, will be the discussion on Hess's law. So we'll work the first delta H problem in the packets. I'll put them up on the board behind me. Also show them on the board, or show them on the computer screen so you can see them if you need to see them. And we'll talk about the two different ways to solve it, and also how to solve it if you're just given tables. That's the super easy form, which is why I save it for last. And hopefully that'll put you on good footing for doing the discussion boards. And you're very welcome. The discussion board Thursday, again, you have until Monday to do it. I don't do the attendance till Monday, so if you need the weekend to work that problem, please take the time to work the problem. That will be perhaps the hardest question you see on the test 3 exam. Is a Hess's law problem with H, Gibbs, and finding the entropy. It's the last question, so not trying to surprise you. Just particularly with that problem, it's very important you show your work. There are a lot of ways to make mistakes with these problems. You'll probably even see me make a mistake doing it on the board. Showing your work is where you can get most of the partial credit from if you can't get the answer. But again, the big thing here is just showing your work for these problems. And yeah, I will see you all tomorrow. Thank you all for showing up.